In this second EnerCmed training session, we move from why nature-based solutions matter for renewable energy communities to how they can actually be integrated in practice. In the previous module, we discussed how NBS help mitigate the urban heat island effect, reduce cooling demand, improve renewable energy efficiency, and strengthen climate resilience in vulnerable urban areas. In this session, the focus shifts to implementation. More specifically, we will explore how municipalities, energy communities, and local stakeholders can follow a structured, step-by-step process to select, design, and integrate nature-based solutions within renewable energy communities in a realistic and effective way. Before going further, it is important to briefly situate this training within the EnerCmed project. EnerCmed is an Interreg Euro-MED project that aims to promote the energy transition in port hinterlands through the development of renewable energy communities integrated with nature-based solutions. The project recognizes that energy transition in these areas cannot be addressed through technology alone. It must be combined with spatial planning, climate adaptation, and social inclusion. The project is implemented in residential areas of port cities across Spain, Croatia, Greece, and Italy, focusing on territories that often face high environmental stress, social vulnerability, and energy poverty. Through training, capacity building, and technical assistance, EnerCmed supports municipalities and local stakeholders in translating these integrated approaches into practice. The objective of this training module is to provide a practical, step-by-step guide for integrating nature-based solutions into renewable energy communities. The focus is on three key dimensions. First, spatial integration, how NBS can be embedded within the urban fabric and aligned with existing land uses. Second, technical feasibility, how to ensure that solutions are realistic, maintainable, and effective. And third, stakeholder co-design, how local communities, REC members, and public authorities can actively participate in shaping these interventions. Throughout the session, we will also highlight methodologies for assessing the effectiveness of NBS, particularly in terms of improving energy efficiency and reducing cooling demand in urban areas. Before diving into the implementation process, let's briefly recap the key messages from the previous training. We saw that nature-based solutions mitigate urban heat island effects and reduce cooling demand in buildings and public spaces. Lower ambient temperatures improve renewable energy efficiency, especially photovoltaic performance. NBS also enhance climate resilience by protecting energy infrastructure from extreme weather events. We discussed how water-based solutions support both cooling and stormwater management, while vegetation-based solutions deliver strong energy, environmental, and public health co-benefits. Importantly, NBS help reduce energy poverty risks in vulnerable REC neighborhoods and transform RECs into multi-benefit, community-centered systems. This session builds directly on these conclusions by explaining how to turn them into concrete actions. Now that we have established why NBS matter, let's look at how these ideas can be implemented through a structured project cycle. Within EnerCmed, we propose a clear and iterative NBS project cycle to ensure that interventions are well-organized, inclusive, and impactful. The cycle begins with engaging stakeholders, working closely with local communities, policymakers, businesses, and experts from the very start. The next step is assessing current issues, such as identifying UHI hotspots, energy poverty, and infrastructure vulnerabilities. Based on this assessment, the project moves into planning, where clear objectives are defined and suitable NBS interventions are selected. This is followed by action planning and implementation, where solutions are designed in detail and executed on the ground. Finally, monitoring and evaluation ensure that the interventions are delivering the expected benefits and allow for adjustments and learning over time. This cycle is not linear but adaptive, supporting continuous improvement. The first and most critical step in the NBS project cycle is stakeholder engagement. Successful integration of nature-based solutions in renewable energy communities depends on early and meaningful involvement of all relevant actors. This includes municipalities, REC members, residents, SMEs, utilities, NGOs, and research institutions. Special attention should be given to vulnerable groups, such as elderly residents or low-income households, who are often most affected by heat stress and energy poverty. Participatory workshops, focus groups, and co-design sessions help align NBS objectives with community needs and REC priorities. Early engagement with policymakers and planning authorities is also essential to ensure regulatory compatibility and long-term viability. Once stakeholder engagement is in place, the next step is to assess current conditions and challenges. This involves mapping urban heat island hotspots using temperature data, satellite imagery, or urban climate models. It also includes assessing cooling energy demand and identifying seasonal peak loads within REC areas. Equally important is identifying areas with limited green and blue infrastructure and analyzing indicators of energy poverty, such as cooling affordability and housing quality. Finally, existing energy infrastructure should be evaluated for vulnerabilities to heat or flooding, alongside a review of urban plans and land use constraints. This assessment phase provides the evidence base for informed decision-making. Based on the assessment, the project moves into the planning phase. Here, clear and measurable objectives are defined, for example, reducing local temperatures, lowering energy demand, or improving photovoltaics efficiency. Priority areas for intervention are selected based on vulnerability and potential impact. At this stage, it is important to align NBS interventions with existing urban development and climate adaptation plans. Identifying synergies between NBS and REC energy assets, such as photovoltaic systems or shared infrastructure, helps maximize benefits. Cost estimation, funding opportunities, timelines, and responsibilities among partners are also established during this phase. Action planning translates strategic objectives into concrete design decisions. This includes selecting appropriate types of nature-based solutions, whether vegetation-based, water-based, urban design, or hybrid approaches. Technical specifications are defined, such as plant species, soil types, water retention capacity, and materials. Spatial layouts are designed at neighborhood or block scale, ensuring that NBS are effectively integrated with buildings and energy systems, for example, shading buildings with PV installations or cooling substations. Maintenance requirements, long-term management, accessibility, inclusiveness, and public safety are all addressed at this stage. The final step covered in this part of the training is implementation. This phase involves close coordination with municipal services, contractors, and local businesses. Green infrastructure, water-based solutions, and urban design measures are installed in public, shared, or REC-owned spaces. Equally important is maintaining communication with residents and REC members throughout implementation. Transparent communication helps sustain engagement, build trust, and reinforce the sense of collective ownership. Implementation marks the transition from planning to tangible impact, setting the stage for monitoring and evaluation, which will be discussed in the next part of the training. Once nature-based solutions have been implemented, monitoring and evaluation become essential to understand whether the interventions are delivering the expected results. Monitoring focuses first on temperature changes and microclimate improvements, helping us assess how effectively NBS mitigate urban heat island effects at the local scale. At the same time, it is important to track changes in cooling energy demand and peak loads within the renewable energy community. Beyond demand, evaluation also looks at photovoltaic system performance and overall renewable energy output, since lower ambient temperatures can directly improve efficiency. For water-based solutions, stormwater retention and flood risk reduction are assessed. Finally, collecting feedback from residents on comfort, usability, and perceived benefits ensures that social impacts are captured. These results are then used to adapt, improve, and scale up NBS interventions over time. Monitoring and evaluation feed directly into a process of feedback and learning. Documenting lessons learned and best practices allows municipalities and RECs to understand what worked well and what needs improvement. Sharing results through the EnerCmed knowledge sharing platform helps transfer knowledge across cities and regions. Most importantly, evaluation outcomes should not remain static reports. They should actively inform new planning cycles, reinforcing the idea that NBS integration is a continuous, adaptive process rather than a one-off intervention. At this point in the training, it is useful to introduce a practical tool that supports implementation, the NBS REC checklist. This checklist provides municipalities and local authorities with a structured guide to systematically integrate nature-based solutions into renewable energy communities. It translates the project cycle we discussed into concrete steps that can be followed in real-world contexts. The purpose of the checklist is to support climate resilience, energy efficiency, and social inclusion at the neighborhood scale. Rather than prescribing fixed solutions, it helps decision-makers ask the right questions at each stage of the process. When selecting nature-based solutions, environmental criteria are a key starting point. First, NBS must contribute to reducing urban heat island effects, for example through green roofs, urban green spaces, or shaded corridors. Second, solutions should enhance local biodiversity, supporting ecosystems rather than simplifying them. Finally, improving air quality is an important co-benefit. Vegetative barriers and green infrastructure can help reduce pollutants and create healthier urban environments. Environmental performance is therefore central to both climate mitigation and adaptation objectives. Beyond environmental benefits, NBS selection must also consider socioeconomic criteria. A key priority is the reduction of energy poverty, particularly in vulnerable neighborhoods. Solutions that lower cooling demand or improve insulation can directly reduce energy costs for households. Social acceptance and participation are equally important. Community involvement increases trust, ownership, and long-term success. Finally, nature-based solutions should support health and well-being, providing accessible recreational spaces and improving overall quality of life in urban areas. Technical feasibility is another critical dimension in selecting appropriate NBS. Solutions must be technically viable under local climatic, spatial, and regulatory conditions. Maintenance and longevity are also crucial. Low-maintenance options, such as native plant species, are generally preferred. Scalability should be considered from the beginning. Modular or replicable solutions can be extended to other neighborhoods or cities, increasing overall impact. Economic considerations play an important role in decision-making. Both initial investment costs and long-term operational costs need to be evaluated. Nature-based solutions often offer cost savings over time through reduced energy demand and lower maintenance needs. Return on investment should also be assessed, including indirect benefits such as energy savings, improved property values, and avoided climate-related damages. These economic benefits strengthen the case for integrating NBS into renewable energy communities. Climate resilience is a cross-cutting criterion that connects all previous dimensions. Nature-based solutions should be adaptable to climate change, capable of performing under future weather conditions. They should also help mitigate extreme weather impacts, for example by managing stormwater and reducing flood risks through permeable surfaces and green infrastructure. By enhancing resilience, NBS protect both urban spaces and energy systems from climate-related disruptions. This slide provides an overview of water-related nature-based solutions and their role in UHI mitigation. Solutions such as rain gardens, bioswales, permeable pavements, urban wetlands, and water retention systems address multiple challenges simultaneously. They support stormwater management, reduce flood risks, improve water quality, and contribute to local cooling. Successful implementation requires collaboration between urban development professionals, local authorities, and technical experts. These solutions illustrate how NBS can deliver multifunctional benefits when integrated into urban planning. To conclude this section, we turn to a concrete example from the EnerCmed project, the Valencia pilot. 2 pilot interventions were implemented in vulnerable maritime neighborhoods, Nazareth and Malvarosa, focusing on schools as priority sites. At CEIP Ballester Fandos, the installation of a bioclimatic pergola significantly improved thermal comfort, reducing UTCI values during peak hours and shifting heat stress from extreme to moderate levels. At CEIP Ajas March, a participatory diagnostic process is ongoing, involving teachers, students, families, and the school board. Here, NBS options are being co-designed to address lack of shade, accessibility challenges, budget constraints, and local ecological conditions. These pilots demonstrate how a structured, participatory approach to NBS integration can deliver measurable climate benefits while strengthening community engagement. We now turn to the Genoa pilot, which illustrates how nature-based solutions can be integrated in dense urban settings with limited space. At the Domenico Ferrero School, an educational garden has been designed not only to increase green areas, but also to actively involve students in environmental learning. The intervention focuses on a west-facing elevated terrace, approximately 6 meters above ground, which experiences high solar exposure and limited wind circulation. The existing heat-absorbing surfaces and lack of shade cause significant thermal discomfort, especially during peak summer hours. A detailed microclimate assessment shows that the area is naturally shaded only until around 11 o'clock, with peak solar exposure between 12 o'clock and 1400 hours. The NBS design is plant-based and literature-informed, combining climbers, Mediterranean shrubs, and seasonal vegetation. Plant positioning is strategic. Sun-loving species are placed on west and south exposures, while shade-tolerant species are used in protected zones. The project is in an implementation-ready phase, with site analysis completed, school engagement secured, and authorizations requested. Expected outcomes include improved thermal comfort, reduced surface temperatures, and enhanced environmental education for students. The PULA pilot demonstrates how small-scale nature-based solutions can improve thermal comfort in public spaces. At Narodny TRG in PULA, the intervention focuses on greening a bus shelter through the installation of 6 planters with climbing plants. The planting system has been carefully designed with drainage and root barrier layers to ensure durability and low maintenance. The main objective is to improve thermal comfort for public transport users while mitigating urban heat island effects in a highly exposed urban location. A key feature of this pilot is the simulation-based evaluation, using computational fluid dynamics to assess microclimate impacts. Different NBS scenarios, short vegetation, green walls, small trees, and large trees, are compared against a base case to identify the most effective configuration. The project is currently in the procurement phase, initiated by IRENA, with technical simulation support ongoing. Despite constraints, such as an advertising billboard limiting the intervention area until the end of 2026, the pilot demonstrates a scalable model for small-scale, high-impact public NBS. To conclude this training module, it is important to reflect on the key messages that emerged throughout the session. We have seen that integrating nature-based solutions into renewable energy communities requires more than selecting individual interventions. It requires a structured process, combining technical analysis, spatial planning, and meaningful stakeholder engagement. The EnerCmed project demonstrates that when NBS are integrated systematically, they can reduce urban heat, improve energy efficiency, strengthen climate resilience, and enhance social inclusion, particularly in vulnerable port hinterland areas. Most importantly, NBS help transform renewable energy communities from energy-focused initiatives into multi-benefit, community-centered systems that respond to real local needs. Building on these conclusions, the next step is moving from knowledge to action. A priority action is to evaluate urban heat island hotspots in port hinterland areas, particularly near renewable energy communities. These assessments help identify locations where cooling demand and heat stress have the greatest impact on vulnerable populations. At the same time, it is essential to engage local communities and stakeholders early in the process. Community involvement in planning and implementation increases acceptance, ownership, and long-term sustainability of both NBS and REC projects. Finally, municipalities are encouraged to leverage support from the Knowledge Facility Instrument, using its technical, legal, and financial expertise to address implementation challenges in complex urban contexts. The next set of actions focuses on implementation and scaling. Municipalities should prioritize the deployment of nature-based solutions in identified hinterland hotspots, such as green roofs, urban greening, and cool pavements, to reduce urban temperatures and energy consumption. It is equally important to monitor the impact of NBS on REC performance, establishing clear KPIs related to energy efficiency, cooling demand, and overall system performance. Finally, successful solutions should be replicated and scaled up. By sharing best practices across pilot cities, EnerCmed supports the transfer of NBS REC integration strategies to other port hinterland areas across the Mediterranean region. Thank you for taking part in this EnerCmed training session. For additional resources, detailed methodologies, and pilot examples, you are invited to visit the EnerCmed knowledge sharing platform using the QR code provided. We look forward to continuing this learning journey together in the next training modules.